per day as given in the question. There are say 3 labors in this company, for example. So 40 hours per day they can work, which could be made available to the company. And now this is the selling part. So one mug has been sold to say $50, and one ball costs $40. Now, just by keeping in view these two constraints, how can you model it? It's like, let us say what the number of balls and number of mugs are our constraint, objectives to find. So we have to take two different variables, say x1 and x2, indicating the number of mugs and number of balls. So that is what we have done here. X1 is the number of balls per day. X1 is the number of mugs produced per day. These are called the decision variables. We need to consider that one first. The resources available, which is the constraints maximum availability of the labor and the clay. Then after the objective has been fixed in this way, if X1 is the number of balls produced, then $40 by selling one ball, then we obviously can have 40 into X1. Similarly, plus 50 into X2, which need to be maximized. Now we have to maximize this profit Z. So the resources available just by depending upon the table which is given to you is 1x1 plus 2x2 is less than equal to 40, which is in this column 1x1, and 2x2 is less than equal to 40. Similarly, the other one is 4 by considering the second column 4x1 plus 3x2 is less than equal to 120. So this is how we can structure, we can model the optimization problem. So this is the objective function, these are the constraints, and these are x1 x2 cannot be negative, of course, because the number of clays, number of labors, or the hours that is required for the labors cannot be negative. That's why they are non-negative conditions. So all these three combined together will give you the structure of the optimization problem in this way. So that is what is the modeling. The second important part is if there is a single variable optimization problem and which is non-linear, then how can you handle that one? Non-linear means it is not obviously a straight line in the Cartesian plane. We have to go for a curvical structure, and we have to think of how to optimize that one. Of course, you can start with a single variable first, then we will jump to the multivariable. So in non-linear programming problem, especially, we can have a concept of bracketing the optimum solution. So exhaustive search, bounding phase are the methods where the optimum value is going to be bracketed, and there are some region elimination methods which are like interval hopping method, Fibonacci search method, golden section method. Now, in general, the general assumption for this single optimization problem is it should be a unimodal function, and it should be a minimization function. Of course, maximization function can also be transferred to or converted to minimization problem. Now look at to this function. For this, all these methods I'm going to discuss actually one by one in a very lucid way, very brief way, so that you can have an overall idea how the single variable optimization techniques can be applied. But most importantly, these optimization problems can be hybridized to some of the evolutionary optimization techniques where we can deal with the concept of making silent to all the variables except one, and we have to start searching in a single direction, maybe it is unidirectional search. So in that case, we can use this single variable optimization problem in a better way while hybridizing the optimization techniques of the nature inspired algorithm with some of the single variable optimization technique. Now look at this assumption actually while reading all those optimization techniques, which is of single variable natured one. In that case, we can have a unimodal function where only the optimum solution is one. That is one modality, or we can say the mode is one, and it is having exactly one global solution, either minimization or maximization. But this graph, there is only one global minimum present in this. That's why it is called unimodal function. So just to understand the techniques of the single variable optimization problems, the global optimal solution should be unique. That is what is said as an assumption. Then only you can read all those techniques. Similarly, it should be a minimization problem because all those techniques have been taught to you, or it can be exercised to the minimization problem only. If it is a maximization problem, you can always convert to that one by multiplying to -1 to minimization one. Then we can have the optimization solution like x1, x2, all these variables remains the same, but the objective function value is going to be negative. Now, with this assumption, we can start with the exhaustive search method, which is the part of the bracketing method. This exhaustive search method says that how can the main target is to find this point on x-axis. So what is this point where the function gives your minimum value? So this the function is, of course, is y equal to f of x. So in this unimodal function, in exhaustive search, what we have to do is first we need to divide the entire search space AB, because AB is the search space through which we have to search for the optimum solution. So out of this, the entire search space, we have to divide them into parts, and they are equispaced. We have to find the delta x value, which need to be added to A to have this point. Then after, you keep on adding delta x every time to get the next intermediate, immediate next interval. So delta x can be found out by dividing n to the entire interval b minus a. That means if you are interested to have n different parts of the entire search space, you have to divide that entire search space to n to have delta x part. So this is the technique. And x star, of course, you can see that there is a star here. I can erase this one. There is a star here. The star represents actually the optimum solution, x star. Now, after finding this delta x, you have to keep on adding them. And first, initially, you have to assume that the first 3 points are x1, x2, and x3. Now, depending upon this, whether the function value at x2 is less than both the function value of x3 and x1, then we have to think that x star always lies in between x1 and x3, because we can make a bracket and the rest of the part can be omitted automatically. So the search space is going to be reduced much. So if it is not, then we have to check again the other condition to shift it towards the right, x1, x2, x3. If the function of x3 is going to be smaller, which is there in the figure itself actually. In this case, actually, this is possible, where the function value at x3 is going to be smaller than the function value at x2, and then which is smaller than again the function value at x1. So this is the case where the points need to be shifted to right. You can see that this x1, x2, x3 is going to be shifted to the right now, x1, x2, x3. Then again we have to do the same exercise whether you have to shift to the right or not. Whenever this condition comes to the picture, then we have to bracket that x star in that particular interval. So finally, the interval is x1, x3, of course, and we have to have a bracket in this way, saying that the optimum solution lies here. But here also x1, x2, after shifting to x1, x2, x3 to the right, then we can feel again the same condition need to be satisfied. Then this set of variables again will shift in the next iteration to the right and right and right. Whenever this optimum solution part is coming in that bracket, then this x3 will be onto the right to this, and x2 may be somewhere here, the x1 may be somewhere here. Then only you can have the condition in this way, so that the function value at x2 is smaller than the function value of x1 and x3, and x2 will be bracketed in between x1 and x3. So finally, we can have a final interval length as twice the b minus a upon n, because b minus a upon n is actually the delta x, and twice delta x will be bracketed, of course, because x1 to x3 will be twice of delta x. They're equispaced. So the next bracketing method is bounding phase method, where the technique goes like this. So first we have to have an initial guess. Let us say that in the search space AB, we are having a guess x0, where we can start our search. But unfortunately, this is having a drawback. If I am having a initial guess which is much closer to x star, then we can say that with a minimum number of steps we can catch hold of that x star quickly, or otherwise we have to take a whole lot of labor to reach to the optimal solution. So it is just the drawback of this bounding phase method, but it works better because we have to have a step size here which is delta. So x0 will be added and subtracted by this delta value, which could be positive or negative. That's why there is an absolute value. So depending upon this condition only, we have to decide whether the delta is positive or negative. The value of delta need to be predefined, which is user defined actually. You can take a smaller delta to have a more accurate value, greater delta to bracket it quickly, but the accuracy will be less. So you should make a balance of taking the delta value accordingly. Then after, we have to go for the other condition where the left hand side is going to be less. The function value at the left hand side will be going to be less than the function at x0, and which is again less than the function value to the right hand side. So if it is the case, then the delta is negative. So it indicates that the graph will go like this. Then only the function value is less than the function value at x0, then after, which is again less than the function value at the right hand side. Now, if this is the curve, then it indicates that we have to go towards the left. That's why the delta is negative. And this is the case, means we have to go to the right because delta is positive. So ultimately, we are going to proceed towards the optimal solution x star. So this is the next, I mean, in the next x iteration, while I am calculating the next x, that is x1, we have to keep the value of k0 fixed. So if k equal to 0, then we have the next iteration, we have the value of x as x1 is equal to x0 plus 2 power 0 into delta. So after finding this delta value positive or negative, we have to move towards the right or left. And once the delta is fixed, then we have to go for 2 power 0, that is 1 into delta. That means 2x0, we are just adding the delta value. In the next iteration, again, we are going for 2 power 1, that is twice of delta value, and thrice 2 power 2, that is 4 times of delta value, and so on. So exponentially, the delta value will be increased. So the step size is going to be increased from time to time. So in that way, we can find a bracket quickly to bracket the solution ultimately. So the final interval will be actually xk minus 1 to xk plus 1. And of course, as I said to you, that the larger delta will give you a poor accuracy in bracketing, but it should be faster. But if there is a smaller delta, the better accuracy you can obtain in bracketing, but it is slower. So we have to make a proper balance to have a delta value accordingly. Then the most important thing is region elimination method. In region elimination method, you can find the bracket or find the optimum solution more quickly by eliminating the regions which is not required actually. So in fact, if the function value just there are 2 points x1 and x2 in the surface, there are a and b. This is a and this is b. X1 is somewhere here which is greater than a, and x2 is somewhere here which is greater than x1 but less than b. Now the condition says that if x1 less than x2 is less than b, then the function value of x1 is greater than f of x2. Then of course the curve looks like this. Then the optimum solution is supposed to be on the right hand side. So this part is not required more. So ultimately the ax1 part is going to be eliminated. That's why it is called region elimination method. Similarly, if I will go for the other way around, that is the function value of x1 is less than f of x2, the graph will look like this, and ultimately the x2b will be eliminated. Or otherwise, sometimes if the condition is like if both the function value are going to be equal at x1 and x2, then you can say that it is in between x1 and x2. That's why ax1 part and x2b part both are going to be eliminated. These are the three important aspects of the region elimination based on which all these methods are developed. First method is interval halving method of region elimination. In interval halving method, we have to take the half midpoint of a and b. So every time we have to reject, or we have to eliminate half of the region. That's why it is called interval halving method. So AB is the surface, X star is the optimum solution which is not known to you. You are searching to that X star, but we have to take the first the XM, that is the midpoint of A and B. Then after we have to take the midpoint of A and XM, and also the XM and B. So L is the entire length, that is B minus A, but X1 can be found out just by taking the fourth, 1/4 part of this L to be added to A. Similarly, X2 will be found out just by subtracting that L by 4 from B. Now, if this is the condition, if f of x1 is less than f of xm, so we can think of the structure in this way, that it is coming down. That's why B will be shifted to xm, and xm will be assigned to x1. So the new B will be xm, new B will be xm. So B is going to be now assigned to xm, so xm will be assigned to B now, and x1 will be assigned to xm now. So xm is having a new value x1 now. So this has been shifted towards the right automatically. So the new value of xm is x1, the new value of B is going to be xm, so xm is going to be this part. So ultimately this region, entire region, is going to be eliminated. That's why the half of the region is going to be eliminated in this interval halving method. Similarly, the other one, we can eliminate the rightmost part if the condition is changed. Now, we can go for the other method called Fibonacci search method, which is quite interesting, where you can have a Fibonacci series in this way. Fn is equal to Fn minus 1 plus Fn minus 2, where n starts from 2. Of course, F0 and F1 both are 1. So we can start with 1. F0 is 1. This is F0. Then after F1 is again 1. When F2 is again the sum of F0 and of F1. F1 n is equal to, you can put n is equal to 2. So F2 is equal to F1 plus F0. So you have to take the sum of the previous two numbers, that is 2. 1 plus 1 is 2. Then 2 plus 1 is 3. Adding these two, I am getting 3. Then adding these two, I will get 5. Then adding these two, I will get 8, and so on. So this is the Fibonacci series where you can name them as F0, F1, F2, F3, F4, F5, F6, and so on. So this is the Fibonacci spiral. How can you get this one? I will tell you here that if I will take these Fibonacci numbers in this way, like if I will go for say small square of length 1. So this is 1, this is 1, and I am going to make another one here adjacent to this. Then this the entire length is going to be 2 now. This is going to be 2 now. Then I will construct again a square of side 2. So because this entire side is 2 and I am having another breadth as 2, then we can have a square of length 2. Now, if I will start constructing the same thing, because the entire length now is 3 and I'm coming down and I'm trying to construct another, another square which is having the length 3, because this is 3, 2 plus 1 is 3. Similarly, if I will go to the left, then I have to extend, because this is 1 and 1, 2, and this is 3. So this entire length is going to be 5. So I have to go for a length of 5 units there to have a square now. Okay, so this is now is having the length 5. Okay, once I'm getting this one, I can go up. Again, this is 5. This is 1 plus 2, 3. So the entire length is going to be 8 now. 5 plus 1 plus 2, 8. So I have to construct another square of length 8 there. Then after, this is 8, this is 3, so 8, then plus 5, 3 plus 2, that is 5, this length is 5, this length is 8, so 8 plus 5, 13. So I have to construct another to the right, the square which is having a length 13. Okay, so this is how we can start with 1, then 2. These are the sequences. Then 3 length, then 5 length, then 8 length, and then 13 length. And we can start from this point only to go to proceed as a. Let me change the color so that you can realize that one. By taking the another color, I can draw the spiral in this way. You can start from here, just join the corner to corner and jump to the other corner with a cortical structure smoothly. You can join the corners to have a spiral in this way. So that is what is called a Fibonacci spiral, which has been shown in this graph. And you can keep on continuing this one because it is dot dot dot. You can have the numbers in this way. That is called Fibonacci spiral. Is having plays an important role in the nature. Let us see how this golden number is coming to the picture. So if I am going to put a point here in between these 2 points, so how can you decide which one is the point, so that the ratio of a plus b to a, that the entire ratio, if this is a, this is b, if the entire ratio like a plus b to a is same as a to b, how can you decide this point? How can you judge this point so that the total length to a is equal to the a to b? So that is what is your main objective. That is a plus b by a should be equal to a by b. Now, just by taking a by b is equal to 5, then I can have a structure here like a by a is 1 plus 1 upon 5. So we can have, after calculating this one, in terms of 5, you can convert the entire thing, that is 1 plus 1 by 5 is equal to 5, and try to solve this one just by taking the LCM on the left hand side. So we'll have a 5 plus 1 equal to 5 square. So it is a quadratic equation where you can find the 5 value as 1 plus root 5 upon 2. So I can have the value as 1.618, which is called as the golden number after solving this one. But this golden number, if I'm taking the inverse of that golden number, we can have only the decimal part, that is 0.61803 and so on. So it's the beauty of this golden number, and we will see that concept in the nature even, the golden number and also the Fibonacci spiral. We can see that in this we can have a Fibonacci spiral pattern in the nature. Okay, similarly in cells also there is a Fibonacci spiral pattern. You can find it in the cells too. Similarly, you can have some of the petals in the flower. You can have a petal of Fibonacci spiral. If I will have a pentagon like this, and we are going to have a, David star inside it, then we can have the A to B ratio. If this is 1.618, then I will have the value 1 here. So it is in the ratio of 1:1.618. Similarly, if I can see hairs coming out from the water after the bath, we can have a pattern like this. It also makes a Fibonacci spiral structure. Similarly, if I will go for calculating this navel part in the body, to the upper part it is 1.618, and this is 1.618, whereas up to the neck, whereas upper part is 1. Similarly, up to the knee from the foot, you can have this part is 1, and this to navel part is 1.618 for all, all I can say unbiased structure of the body. Now, so these are some of the structures where you can also consider the hand from top of your finger to the wrist. You can have this one part, whereas approximately up to the elbow you can have it is up to 1.618 ratio. So similarly, you can have also a Fibonacci spiral in the ear structure. So all these are coming altogether. The nature is plenty of mathematics, and this golden number plays an important role in the nature. Now this Fibonacci search has been implemented in the optimization. It is named as Fibonacci search method. Let us see that if X star is the the optimum solution of this inside this search space, we have to make the target to get X star. L is B minus A, N is the number of function evaluations. We need to fix it before we start. The function evaluation means how many times you can call the function while solving it in the algorithm. So LK star we have to calculate here. LK star will be based on the Fibonacci number only. If k is equal to 0, let us say, and n is equal to, say, k is equal to, say, 0 and n is equal to 1. So you can have a structure here like n is equal to 1. So 1, 1, 2 minus 0. So F2 upon F2. Okay. If I will go for, this is 1. Now, if I will go for k is equal to 0 and n is equal to 2, then F3 will be in the denominator. And in the numerator, I will have n is equal to 2 plus 1 is 3 minus 0 is F3, and so on. But k will vary again from iteration to iteration. If I will go for k is equal to 1 instead of 0, then I will have here 1, 1 cancelled out. So this will be F2 divided by F3 for n is equal to 2 and k is equal to 1. So that means we can take the fraction of two consecutive Fibonacci numbers. F2 is in 1 and F3 is going to be 2 there, because F0 is 1. So that is something like half of L. We are going to get the value of LK star as the half of L. Similarly, keep on doing the same exercise. You can have something like if k increases to, say, 2, then I can have one more there. So F2 will be divided by, say, F4 and so on. So accordingly, the length, the difference of this Fi's are going to be more and more, and we can have the fraction of L a bit smaller and smaller. Accordingly, you can have new LK stars every time. And accordingly, you can have a step length to jump from the x1 to x2, x2 to x3, and so on. So k is actually started from 2, of course, because we can have a increment of 2 there, and then after based on the Fibonacci numbers, you can manipulate all these values of x1, x2, and so on. So the beauty of this is the function evaluation required in each iteration is only one. That's why it takes less time than the other methods we've discussed earlier. Now, this is a faster than the interval lapping method, of course. But the last method we are going to discuss is region elimination method. In the region elimination method, we can find the golden section method. Golden section method says that we can have a mapping from this x-axis to double axis by using the this equation w equal to x minus a by b minus a. If I am taking x value as b, obviously the w value is 1. If I will take the x value as a, obviously this is a by b minus a, that is a minus a by b minus a is equal to 0. So this a b value is mapped to 0 1 value. So there is a mapping to this. It is sometimes you call it as a normalization, and this value are named as a w and bw. So all the values we are going to get is in between 0 and 1 after mapping, and LW is actually the length from AW to BW. L is the length from A to B, and W1 can be calculated just by using this golden number, inverse of this golden number. So that is phi inverse AW plus 0.618 LW. It says that W1 you can reach somewhere here, which is actually 61.8% away from AW. So you can have a point over here as W1. Similarly, W2 can be found out just by subtracting 61% of LW from BW to get a value somewhere in the left, that is W2. So the most beauty of this is, if I'm taking the next iteration, this W1 will be either assigned to BW, or W2 will be assigned to AW, so that one region will be eliminated. The beauty of this is we have to evaluate only one function. So let us say if AW has been transferred to this in the next iteration, then we can calculate the W2 somewhere here. So that means W1, the function value is already been calculated. Only one new function value need to be calculated afterwards. That's why it is going to be faster than interval mapping and also the Fibonacci search method. Now we can slowly move towards the multivariable optimization problem, and there is an involvement of nonlinear programming where which makes the optimization problem more complex and more critical. So we can move towards, because multivariable optimization problem, if it is of 2 variable or 3 variable, you can handle it manually. You have to find the Hessian matrix, then go for the positive definiteness of the matrix. If it is positive definite, then you can think of the minima and maxima, and so on. Many other methods are there which will detect the minima or maxima of that particular function. However, if the number of variables is going to be more and more, all these traditional methods are going to be handicapped. There only the evolutionary optimization methods are coming to the picture, because this evolutionary optimization method, or sometimes it is called as nature-inspired algorithms, they are free of all the radicals, all these auxiliary knowledges, like whether the function is differentiable or not, whether the function is continuous or not, doesn't matter. You just keep picking all the functions and just feed all the evolutionary algorithms to solve it, because it is a probabilistic technique. Many random values come into the picture. We have to generate that one in a population, pick the right one or the correct one depending upon the fitness value, then go for the better solutions afterwards. So that's why the evolutionary optimization nowadays becomes popular. So instead of discussing all the traditional methods in the today's lecture, let me focus on some of the evolutionary optimization techniques quickly. So in our evolutionary optimization, as you know that evolutionary means gradual development, optimization means either minimization or maximization. So just to reach to the global optimal solution, there should be a gradual development in the algorithmic steps, so that slowly and steadily will move towards the optimal solution. Of course, you know that there are two terms called global and local. So out of the entire source space, say from A to B, I have to find the global optimal solution. That means in the entire source space, I have to take the best maximum. That is called global maximum. Of course, some of the more maxima are present there, also, which are called local maximum. This is maximum in this neighborhood only, not in the entire search space. But in the entire search space from here to here, you can say that the best maximum is this one. That's why this has been treated as global maximum. Similarly, the minimum. So global minimum is the overall minimum, and the minimum which are there in the neighborhood is called local minima, which is actually written in the definition too. But our main focus is to catch hold of this global maxima rather than the local maxima. We are not interested for these local ones rather than the global ones. So the global maxima and global minima are our main focus in this approach. So just to find this global optimal solution, the global maxima and minima, there are two types of different approaches. One is deterministic approach and otherwise probabilistic approach. Of course, the deterministic approaches include all those techniques which we are reading in the books. That these are the traditional methods. But in probabilistic approaches, there are endless. We can say many of quite a large number of optimization techniques yet developed, like genetic algorithm, memetic algorithm, Drosophila food search optimization, tau search optimization, ant colony optimization, artificial bee colony optimization, particles optimization, bacterial foraging optimization, differential evolution, etc. So many more are there. But all these are based on the genetic algorithm because it has been developed in 1975 by John Holland, who was a professor in Michigan University. Of course, I got a chance to meet him in 2006 at Las Vegas, USA, in a talk when I visited USA during my PhD period. So the talk was actually memorable. He started talking about the genetic algorithm, how it has been started and developed. And of course, this memetic DF and all these algorithms are based on those population structures just by modifying all the internal operative system. Now, these nature-inspired algorithms are actually different than the traditional methods because the parameters are directly used in the traditional methods. But here we need to encode it, either a binary or hexadecimal or decimal encoding system. We have to code them first. The traditional methods, the search starts from a single point where the population of points are required for the nature-inspired algorithms or evolution algorithms. As I said to you that some of the auxiliary knowledges are required for the traditional methods like differentiability and continuity, but it is not required here at all. Only the payoff matrix, that is the objective function value required in the nature-inspired method. Of course, this is probabilistic, but the traditional methods were deterministic. So you have to take some probabilistic transition rules. I will show you some of the steps actually, how the probabilistic transition rule are coming to the picture. Of course, without going all details to all the algorithms, let me quickly go through the basic idea of the genetic algorithm. Then after we can think of some new techniques, new algorithms which has been developed. And finally, I will conclude with an application to a Sudoku puzzle solving, where which is a common interest, of course, I think, because I can understand that a heterogeneous group of faculty members have joined to this workshop. So I have taken a subject which is a common interest called Sudoku puzzle solving. I will give a new technique idea to solve the Sudoku puzzle solving, how I have developed that Sudoku puzzle to an optimization problem, and how I have used in my research to solve it. So that will might be giving you a boost or giving you an idea to construct a new technique which is more suitable towards your research optimization problems which you have developed in your research areas. Now, let us start with the basic ideas of genetic algorithm quickly. Those who are not aware of the genetic algorithms, listen carefully because I will give some basic ideas with a small example so that we can understand in a better way. Now, this encoding, selection, crossover, mutation are the basic steps of genetic algorithm. We will go these steps one by one. Of course, this elitism is optional. We may use this one or may not. I will tell you what are they, of course, but encoding, selection, crossover, mutation, they are the operators which need to be used cyclically in the genetic algorithm. In the genetic algorithm cycle. Now, let us start with the working mechanism of GA with an example, small example. Let us now think of minimizing this function, 2x1 plus x2q. So this is a function where there are two variables. So I goes from 1 to 2 only here. So x1 and x2, these are called bounds, not the constants. Of course, in the sense of evolutionary optimization, we call it as bounds. So x1 is having a lower bound and x1 is having other upper bound. Similarly, x2 is having a lower bound, that is x2l, and upper bound x2u. So just remember this one. I am not coming back to this slide once again. So this function need to be remembered now, 2x1 plus x2 cube. Now coming to the first step of this genetic algorithm is called encoding system. It's this starts with the population. These are the given data, of course. There are two number of variables, n is equal to 2. The lower bound of x1 is -1, the upper bound is 3. Okay, so lower bound, upper bound have been fixed. Similarly for the x2. Now we have to consider this one from the expertise knowledge. L1 means the string length that we have taken for the x1 first variable. Similarly, the string length for the second variable is L2, that is 5. So it depends upon the sensitivity of the variable or how critical the variable is. If it is more sensitive or more critical or more complex, then we have to take more number of bits for it to have more and more accuracy. But in return, it will consume more time to solve it. So there should be a proper balance or fine tune for that. And similarly, for this PS is actually the population size. I will tell you a bit later. Like the first one, if I have taken for the first variable, I have taken L1 is equal to 4, so there should be 4 bits appear in x1. So against x2, there should be 5 bits. What are they? They are 0, 1 only, because it is a binary encoding system. There are many other encoding system also, which is out of the scope of this lecture. So what I have to do is I have to generate randomly the 0 1s, asking to the computer to generate 0 1s randomly 4 times for x1 and 5 times for x2. So that is called one string, that is string number 1. Similarly, for string number 2, we have to do the same exercise, and similarly string number 3, 4, 5 up to 6. So total number of strings we have taken is 6, that is called population size. The entire thing is called as a population. So this pop size or population size is called is fixed to 6, but in general, researchers say that if there are n number of variables, we need to take 10 times the number of variables as the population size. For example, in this example, actually, x1, x2, there are 2 variables. So 2 into 10, that is 20 number of population size need to be there. But because of the space constraint in the slide, I have taken only 6 to explain you in a better way. After finding this, we can find the corresponding decimal number to this just by converting this to the decimal number, that is multiplying 1 by 2 power 0, 0 into 2 power 1, summing them up into 2 power 2, and so on. So I will have the equivalent number as 13. Similarly for x2 is 5, and so on. So these are the equivalent decimal numbers, but the most important thing is this is not lying in between the prescribed range. So just to bring them into the prescribed range, somewhere it is not lying. So just to bring them into the prescribed range, there is a formula, this one. So that is the normalization formula, where the lower bound need to be added with, let us say this 13 has been changed. This is the matrix we got in the earlier slide. Then this is changed to this. How to do that one? So let me do it here for you. So lower bound here is -1, because for x1, how this has been done, I am just telling you just by using this formula. So the lower bound is -1 plus the upper bound is 3 minus the lower bound, that is minus of -1, divided by 2 power li, the string length for the first variable is 4, we have taken -1 into the decoded value is this 13. So that is how we can convert this 13. This is actually is equal to 2.47. Okay, so that is how we can get this value. Similarly for x2 column, we can calculate all those values. So once I will bring all these things into the range, this is also now in a proper range, then we can have 6 set of different variables. x1, x2, this is one set which can be put in the objective function, which has been taken as 2x1 plus x2q, as you remember. So just by putting these two values in that function, I will have some function values, say 26.89. Similarly, putting x1, x2, these two value for this pair, I will get this function value, and so on. So after calculating this one, there is a process called selection. So of course, I am going to teach you here the selection, which is called tournament selection. In the tournament selection, I have to take the function value only. This is the matrix I have considered in the next slide. So first one will be compared with the second one. The best one will be copied now. So the best one means in the sense of minimization, the 26.89 is the best function value, because the function is a minimization problem. So 26.89 will be picked. Similarly, second with third, so second will be second part will be filled with the winner of the second and third, then third and fourth. So finally, the last and first will be compete together to get these values. So first and second will give you 26.89. Second and third 52.51. So what the interesting thing here to note is that the worst individual is no more exist here, but the better individual, which is having very less function values, have multiple copy in the population. So that is what is called survival of the fittest, Darwin's theory, based on which it is called as genetic algorithm. The best Jo Jita Wahi Sikandar. The best one survives always, but the worst individual dies off. That is the Darwin's theory. So crossover, it is a one-point crossover. What I want to say here is, after selecting all these strings, there is a background running of the binary string, suppose. So there is a binary string corresponding to 26.89. So once we have copied this one, the binary string has been copied to the first string. Similarly, 52.51, 2 times we have copied the second string, and so on. These are the strings corresponding, binary strings corresponding to those values which were there in the background. But in the crossover, one-point crossover, we are now going to have a crossover site out of these two different strings. I have to consider one probability for these two. That probability may be between 0, so it must be from 0 and 1. Let us say that value is going to be 0.6, and the probability of crossover always will be very high, that is near to 1, that is say 0.9 or 0.95, something like that, and it should be prefixed before you start. And if I am considering one pair, first two, and asking that whether the random number generated between 0 and 1 is less than the PC or not. If it is less than, then these two pair, sorry.
Sir, yeah. Can you explain that one more time of that, how you converted to binary?
This string you mean to ask?
This, yes, sir. Yes.
Yeah, in fact, you are not converting. You are not converting actually. You can look at here. This 26.89 is the function value of this pair, and this pair is coming from this pair, and for this pair we are already having one particular string. You can go back. Yeah, this one. This 13 and 5, you can catch hold of these two values. 13 and 5 is coming from these two. Okay. So this is the basic string we have taken. So once I am selecting this function value 26.89, that means I am taking the function value corresponding to this pair. So the corresponding string automatically will be copied. We are not going to convert. The corresponding string is this one. You can look at here. This one is your corresponding string, which need to be copied directly. Similarly, go to the function value, next two function values, this and this. There are two different function values, of course. You compare these two function values. If this is the winner, ultimately this will be copied for the second string, and so on. Got it?
Got it, sir. Got it. Yes, thank you.
Okay, thank you. Now, after copying the corresponding strings, we are doing this exercise. In the PC, we have taken a higher value of PC, and we are taking a crossover site. What do you mean by crossover site? Remember first that that random number we have generated should be less than the PC. Then only we will go for crossover. Otherwise, we will skip this pair and we will go for the next pair. That is the process. So in the crossover, if once we are getting a value, say let us say 0.6, which is going to be less than to the prefixed value, that is PC, that is 0.95, then we are considering that yes, these two will go for crossover. For this pair, we are applying the crossover, means we have to find a crossover site. So how to find this crossover site? There are 4 strings here, 4 bits here and 5 bits here. So in between, so total is 9. So in between there are 8 gaps. Okay, so these 8 gaps are there. This one, and so on. There are 8 gaps. So out of these 8 gaps, arbitrarily you choose one gap, which is here now, this one. So I am just giving a crossover site over there. So then after we will go for the crossover. The crossover sense is that the rightmost part will be swapping. So this 0, 1 will go down, and this 1, 0 will go up. It's called as the crossover. So ultimately this will serve your purpose. Similarly, if I will go jump to the next one and suppose the random number is going to be 0.97 and it seems to be it is greater than the prefixed value, so we are skipping this one. That's why there is no crossover side for the second pair. Coming to the third pair, again we will do the same exercise. Might be there is the random number which has been generated is going to be less than 0.95. That's why there is a crossover side. The rightmost part entirely will be swapped. Of course, in 1 point crossover, the rightmost part can be swapped, or we can keep fixed the rightmost part and left part will be swapped, because we need to make an interchange of the characteristics among the parents. That is what is the main idea of crossover. The characteristics of the parents will be swapped to produce the offsprings or children. So we can see that after crossover, this 1 0 is going up and this 0 1 is going down. So that is actually the process of crossover, but there is no change here because there is no crossover. For this also, again, the lower part is going up and the upper part is coming down. This has been swapped from the original. That's why this is a new set of strings we are getting. Of course, all are not new. Wherever there is a crossover. So if there are 100 pairs, we are expecting to have say 95 pairs to go for crossover. It is something like that. It is not that all the pairs need to have the crossover compulsorily. Now, after getting that string, yes.
Sir, how to decide that PC value?
Yeah, it is coming from the expertise knowledge actually. The researcher says that it should be much closer towards 1. So mostly researchers are taking 0.8 or 0.9. But of course, for your problem, you have to make a fine tune. Just by varying say from 0.7 to 0.95 with an increment of 0.05, you can keep on jumping the PC value and say fine tune that one and see that where it is effective, where you can get much better value. We have to make a fine tune of that. PC. Then we are going to the crossover mutation probability, that is PM. So this PC and PM need to be fine-tuned every time. Okay, so in all the evolutionary methods, all the population-based methods, there are some parameters which need to be fine-tuned. If it is better for say model order reduction problem, might not be giving better result for other scalable problem. It is happening actually. If it is the PC is fixed say 0.7 for one problem, it may not be fixed for it may not give better result for 0.7 PC for the other problem. So you have to again make a fine tuning of that. That is only the drawback in this method actually. But there are certain algorithms which will again find the PC and PM value just by taking the different combinations of PC and PM. Or also you can do that on all combinations. You can take it from your side. But roughly, I can say that you can take some of the values in between, say 0.1, 0.2, 0.3, or 0.4 arbitrarily. But if we are having a conclusion like the greater value of PC is going to give you a better value, then you can keep fixed after say 0.8 to 0.8 to 1. Completely, you can vary just by keeping it in increment of say 0.01. So might be there are say 20 to 30 different points where you can check it to see the fitness values of the function. Again, there are many analysis. It's not like one time whatever the values you are getting may not be true always. Just by varying the PC, you can have different values. For the same PC also, you may not get the same optimum solution. There will be a slight change because it is a probabilistic technique. So then after you can ask me why then we can use this one if the answer is not fixed. Of course, if there is no method to solve it, it is better to have an alternate method to solve thousands of variables at a time, thousands of constants at a time. There is no such method traditionally available in the book. So at least to have a near optimal solution is wise rather than getting nothing. That's why we are using all these optimization techniques. Now, coming to this PM, there is the other one that is called mutation. That is PM is again probability of mutation. So for crossover, we have taken pairs, but for mutation, we are taking only bits. For each individual bit, of course, PM is, as the researcher says, the PM is very close to 0. So sometimes people are taking like 0.01, something like that. You can check near to this value, which one is best fit to this. So for each individual bit, we have to select a random number, say 0.03, something like that. This is a randomly generated number from by the computer. If it is less than this PM, then we have to go for the mutation. But unfortunately, this is greater to the prefix value. That's why we are skipping this one and jumping to the next bit, and so on. So this process will continue for each bit. So if PM is going to be 0.01, we are expecting that 1% of the bits are supposed to be go for mutation. So out of 100, only one bit will be flipped. What is the meaning of mutation? If this goes for mutation, if it is already 1, then it will change to 0. If it is already 0, then it will change to 1. That is only the mutation. That is just a slight flipping or slight perturbation in the population. It's called mutation. So there are also theories why the mutation is going on. So that is a different part where we are talking somewhere in the local minima. It will throw from that local minima towards the global minima by using the mutation operator. So let us say at these two rounded part only, the probability of mutation is going to be greater than the randomly generated number where the mutation happens. That's why this 1 is going to be 0 and 0 is going to be 1. And the corresponding, again we have to do the same exercise. Now nothing new. After getting this new population set, I will have to go for the corresponding real number, as I said to you earlier, by multiplying 2 power 0, 2 power 1 and so on. So I will have some other metrics where there are decimal places, but it may not be in the range. Then to bring them to the range, again the same normalization formula we have to apply. Then after I will get the pairs of x1, x2, then find the corresponding function values. Okay, so after finding this function value, there were a set of function value initially you have already calculated. Now there is another set of function value. Both the function values need to be added together before G and after GA. This is the completion of GA cycle. That is called elitism, the last one, which is optional, of course, but it is always, most of the cases, it is wise to apply the elitism just to retain the best individuals achieved in the population. Now, just by combining these two, we can have a ascending sorting of the function values, because the best function value will be at the top. The lowest function value is the best function value because it is a minimization problem. So after adding them, combining them and taking it a sorting way, the best half will be taken to the next population to be participated. Then after, again we will go for the selection, crossover and mutation. It is a cyclic process. So this will give you the best individuals. So you can see that the worst one which is there, CN, are all automatically die off. The best 6 has been taken after combining these two. It's called elitism and it is a repeated process. So end of the GA cycle is here. After the elitism, this will be again applied as the initial population. Then after keep on doing this selection, crossover and mutation again and again, so that the points are coming closer towards the optimum solution automatically, just by throwing the worst parts and in implementing some of the better individuals inside the population. Slowly the function values are going to be more effective and approaches towards the minimum. So this is how I will tell you how this GA works. This is called a scalable function called sphere function. N could be anything. You can take n is equal to 1000 or something like that. Then you can say that the list will increase like x1 square plus x2 square up to x1000 square. Each individual xi is lying between -5 and 5. Of course, I cannot visualize them if n is going to be greater than 2, but for 2 I can show you in a Cartesian plane. If n is equal to 2, it is something like x1 square plus x2 square. It's the function looks like this. There is a one global minima which needs to be case hold of. But if it is having more than one variable, more than two variables, it is absolutely in 3-dimensional. You can see for 2 variables. Then after it is imaginary. But the most important part here, interesting part here is you can take any number of n. This is actually called a scalable problem if n can be varied to anything, but the optimum solution remains fixed. That is, if it is 1000 even, then you can have the minimum function value 0 at 0, 0, 0. All xi's are going to be 0. Then only the function value is going to be 0. That's the beauty of this scalable problem. This is actually called a benchmark problem, which is easily available on the internet. On Google, you can type sphere function, where you can get the structure of the sphere function as a hemisphere-like structure, where there is one global minima which touches to the floor, and it's our objective to find it out. If you are designing your own algorithm, it is always wise to test your algorithm on those set of benchmark problems available on the internet. Then after, you can apply that one in your own real life problem arising in your research. Otherwise, it is not justified actually. So we have to test if it is effectively working for the benchmark, because these benchmark problems itself, they are critical. They're very complex. If you can fight in them, then you can say that yes, my algorithm is having some strength to fight for the optimum solution to solve them. So I will show you that for two variables only, this x1 actually lies between -5 to 5. Similarly, x2 also lies between -5 to 5. And this is the optimum solution, 0, 0, as I said to you, for two variables for the sphere function. And this is actually the population created. So this a particular value means it is having some x1 and it is having some x2. So x1, x2, that means one string. That means it is one string of the population. So this much number of the dots represents this much number of population size is there. So this much number of strings are initially generated to start with the genetic algorithm. When the genetic algorithm runs, the points are coming closer, closer, and closer, and finally they comes to converge to 0, 0 to stop that. So that is the beauty of this genetic algorithm to approach towards the optimum solution. Some of the alternate popular evolutionary algorithms are there, like particle sum optimization, the ABC, as I discussed to you, SEO, TSO, BFO, and DFO. All these are based on this population optimization, population-based techniques. Now, some of the modern evolutionary optimization techniques have been designed actually. So exploration and exploitation are the two key words to design a new or modern evolutionary optimization technique. Exploration means overall things need to be taken care of. How to search the search space entirely as a whole is called exploration. But in exploitation, if you are near to the solution but you are unable to catch hold of that, you have to exploit that part locally to that is called a hill climbing process. Actually, you can climb the hill, you can go to the up or go to the down according to the maximization or minimization problem respectively. That is called exploration. So keeping a proper balance between exploitation and exploration is the key idea of designing any of the modern optimization technique. Some of the recent research, our recent evolutionary optimizations are looking like this: the Sudoku puzzle solving 2012. There is a retrievable genetic algorithm we have designed. There is a chemo-inspired genetic algorithm for modular reduction in electrical engineering in 2013. In 14, we have designed DFO, that is a Drosophila food search optimization, and we have applied that into constraint optimization problem. Then there is a MCSO, which is applied in the large scale optimization problem. This CSO stands for what is called the M stands for modified, C stands for competitive, S for search, O for optimization. So modified competitive search optimization or SPAM optimization. So LSOP is called large scale optimization problem, which is designed in 2017. In 18, we have designed DPD in the population if there is a whole lot of strings in the population. And it has been divided into three parts. The first part has been applied the DE, the middle part is PSO, and the last part is DE again. So in this way, there is a implementation of DE, PSO, and DE that is called DPD algorithm. And it has been shown that there was a paper called PDP, and to that paper we have countered by saying that no, the PDP has to be changed to DPD, and it has been applied in the electrical networking system where there is a economic load dispatch problem. Thereafter, there is a TSO, that is troop search optimization, has been applied to LJPP, that is a linear zone potential problem. In 2019, there is a list looping method which has been applied to the green vehicle routing problem. Nowadays, we are working on many and multi-objective optimization problem. So all these optimization problem at a time is not possible to discuss, but I will give you some of the ideas, the whole idea about this optimization problem we have developed. The hybrid technique is most effective, and sometimes we are thinking of why the hybrid technique is useful and why you should do this one. Some of the traditional methods approaches I have discussed actually, those can be implemented into the loops of the evolutionary optimization techniques to make the efficiency better. So you can look to this story, that is lame man and blind man. They are going together to see a fair, and the strength of one compensates the drawback of the other in this case. and they want to visit a fair where there is a blind man unable to see anything, and there is a lame man unable to walk, but they both together want to go to the fair. So the lame man who is sitting on the shoulder of the blind man guides the path to the blind man, so that the purpose has been fulfilled. That is actually the hybridization. The purpose has been fulfilled just by taking the strength of the one which compensates the drawback of the other. That is what is the main objective. Sometimes people are directly using two different algorithms to sum them up or merge them up to solve the optimization problems, but that is not wise. GA with vectoral foraging optimization has been hybridized directly, but you can see that the selection is actually the survival of the fittest, where reproduction is having the same idea in the BFO, but elitism is actually retaining the best individual, where elimination dispersal step of BFO is elimination of the strings and simultaneously insertion of the new strings. That means these two are having the same meaning and these two are having the same meaning. Then what is the need of directly hybridizing these two? So only the thing is that the chemotactic step is having its own potential, which is new to explore the search space in a better way than GA. That's why just this chemotactic step has been implemented in GA just to use this one in the hybridization process. That is called CGA. Okay, so CGA is only just by taking the chemotactic step from BFO to merge them in GA to have a hybridization technique, that is CGA, which is available in the now in web page. We can say we can search that chemo-inspired genetic algorithm, which is an Elsevier paper, applied mathematics and computation, has been published. So this has been effectively solved the optimization problems. So this chemotactic step is one of the operator in the GA cycle, of course. And I'm not discussing it more. Actually, it is has been used in the model reduction, where you can see the step response, which is the original step response, the original red line, and CGA is the green line, which is coming closer towards this. Similarly, the red and blue line for the impulse response also coming closer to each other in the electrical system called model reduction problem. Similarly, new design techniques are also sometimes very useful. There is a Drosophila, which is actually a insect which is roaming around the ripened banana. You might have seen that one. It's a black colored insect which is roaming around the ripened banana. It's called Drosophila, starts from D. So DFO is the Drosophila food source optimization. One of my research scholars studied for 6 months on this creature, and this is actually having a very good food source behavior. That's why the food source behavior has been modeled mathematically and has been published in Elsevier, actually, this paper, DFO, which is based on the there are many techniques how it smells out through its proboscis and goes to the sensilla is having its sense to observe the food, and this legend is actually the food amount which has been available outside has been grasped easily through the proboscis to take into the olfactory receptor, and based on which this will take a decision to find the final decision to which food it should move and all. But again, this has been applied to the benchmark functions like the sphere function, Rosenberg function, as I said to you, which are more critical functions, and the convergence is going to be very better everywhere. The black line is DFO, which comes very closer to the optimal solution or closer to the x-axis, that is, or negative towards the negative axis to on y-axis to get the better result. So then another one is troop search optimization. I'm not going in details because a few minutes are left. I can understand. So troop search optimization is actually based on the troops. In troops, actually, the before any battle, soldiers are prepared among themselves, where there is a commander for each troop. Troop 1, troop 2, troop 3. 3 troops are there. There is a commander and there is a captain who is overall leading to them. And what happens actually while there is a soldier injured, then they will be swapped suitably by the other soldiers. Similarly, if there is a part has been damaged by the enemies, then this entire part will be again swapped by the other soldiers, other set of soldiers. That is actually a swapping method. Is called a cut and fill method, which has been applied here. One part of 20%, we have taken the fine tuning of this 20% will be filled by the other part, and those has been developed by this mathematical expression, where this 20% of the population has been cut and will be filled by the fresh candidates or fresh strings generated by this formula. So this is based on this true search algorithm. Then it has been applied to the Lindbergh potential, which is having the interaction between these atoms actually from 3 to 50 number, that is called LJ potential problem, where you can see that TSO is giving better minimum energy in the interaction in terms of electron volts. So the success rate of TS also is better in terms of 100 number of runs, and how many times we are going to achieve the best result has been actually compared with the near competitors like PSO and MI LSPM. Now this multi-objective optimization, I am not going to move in details actually. I will give you a small hint about the multi-objective optimization. If the number of objectives are going to be 2 or more, then we can name it as a multi or many objective optimization academically. In multi, there are 2 objectives, in many, more than 2 objectives. So many objectives, of course, are going to be more critical or more complex than the multi-objective optimization. You can see here that the structure looks like this. The F1, F2, F3, up to M number of objectives are there. Which one may be minimized, other may be maximized, other may be minimized and maximized alternatively, or it's a mixture of minimized and maximization problem. And these are the set of constraints we are having. So these are the decision vectors. This is the decision vector. These are the decision variables, of course. So all these are actually these are having the conflict of interest. Objectives are conflict of interest. Then only you can move towards the objective function. Let us say if we are moving from Allahabad to Delhi, then we have to take some means to travel. Maybe you can go by walk, by cycle, or by rocket. It is up to you. But the travel distance is going to be very faster if I'm taking a rocket. But economically, it is much expensive. Similarly, if I will go by walk, it is very less expensive, of course, but the time consuming, it is much economical. Less expensive is much economical, but the distance traveled is very minimum, so the time requirement is very high. So which one is the best suitable solution? It's very difficult to judge, because this is the best solution if I will consider money. Very less money we have to consume, but this is the best solution if I will consider the time. So you can reach quickly there. So each one is actually a solution. That's why it is called as a pareto-optimal solution. So instead of getting a single solution, we have to have a set of solutions that are called pareto-optimal front. So there are many discussions. I'm just skipping that one to go to the next topic. That is called application of optimization problems. That is called retrievable genetic algorithm to solve a Sudoku puzzle. So it will take hardly 5 minutes to complete it, complete my talk even. The Sudoku puzzle, that is the common interest. I have taken this topic because there is a heterogeneous group as you know. So Sudoku puzzle is actually a common interest of solving this. It is a 9x9 matrix where there are some givens like 9 here, 3 here. We cannot change them. These are the givens. But we can try to fill the rest of the parts which are not givens. But the rule for solving this Sudoku puzzle is you have to apply only the digits from 1 to 9. So there should not be any repetition in the rows, in the columns, also in the subsquares. This is called a subsquare actually. So there are 9 subsquares. In each subsquare there should not be any repetition. So there are Monterey and Coljanon who has already solved this one initially, and I have shown that I have beat their algorithms, and this article also available on the internet. That is retrievable genetic algorithm for solving Sudoku puzzle. Instead of wasting time in telling their technique, better to come to my technique to tell you the methods actually. I will give you only the function value which I have designed in my paper. Let us see that if somebody there is a matrix, that means it is a Sudoku puzzle where there are some givens, like say 8 is a given, we cannot change it. Similarly, 3 is a given, we cannot change it. That is what you can see from this Sudoku puzzle. Of course, this is a solution actually. This is not a question. This is a solution. So in the question actually, this 8 will be given, which cannot be changed, and 3 is a given, which cannot be changed. And rest part is already there, of course. If I will give this question to you arbitrarily, some kid may start solving this one just by putting here 7 arbitrarily. If he is not having any idea, say 8 again, say 4 again, there may be a repeated value also, or it may not be repeated also. So how can you find the fitness of an arbitrary field Sudoku puzzle, and how can you think of genetic algorithms to solve it? That is my main concern to teach you now. See here, if there is an arbitrary values like this, arbitrary, everything need to be arbitrary only, because we are using a retrievable genetic algorithm where everything need to be arbitrary. If I am taking care of all the constraints, all the features which are traditionally solved, there is no use of genetic algorithm there. That's why I started with the arbitrary solving this one. So arbitrary field all the values from 1 to 9 without considering that there is a repetition or not. Now, Ij is one cell, Kl is another cell. I am going to compare this one cell to other cell, and the function contribution is either 0 or 1. 7 is now compared with 8. So Ij is now compared with Kl. If they are equal, then the function value is going to be 0. The contribution of the function is 0. Now this Kl changed. This Ij is going to compare with this 8. If they are equal, then the function value is 0. If not, they are 1. Similarly, this 7 will compare to this 4, then so on. This will continue. After completion of these, then we will catch hold of the second value. This 8 will compare to the next one, then after the next one, then after the next one, and so on. After completion of that, we'll catch hold of the third value, and so on. This is the repeated process for the rows. So 7 to 8, 7 to 5, 7 to 9. So what do we expect? We expect everywhere to get 1 because they should not be equal. If it is not equal, then only the function value is 1. So we are expecting to have 1 everywhere. So just by keeping in mind that every comparison should have a contribution of 1 to the function, I am going to calculate the final fitness function value. So what is the fitness value there? I am going to calculate. So 1 every time I have to have the value. So in the first row itself, there are 9 elements. So out of which 8 comparisons could be possible. So there could be 8 number of ones I am expecting as a final. If it is a final solution, everywhere I will get 1 value because there is no repetition at all. So 8 number of times I am comparing, and everywhere I will get 8. So I can get 1. So the final answer is 8. 1, 1, 8 times. Plus, if I will start from 8, again there will be 7 comparisons. So it will be added with 7. Plus, again starting from 5, there will be 6 comparisons, and so on. So finally, it will continue up to the last comparison, 6 with 2. That is 1. So this will give you 8 into 9 by 2. That is called 9 into 4. 36. So this is 36. So this 36 is the row fitness actually, and that will continue for all 9 rows. So this comparison will be done for all 9 rows. And this is for the rows, but the entire thing can also be done for columns and also for the subsquares. So that's why I multiplied with 3. So that will give you 972. So I have fixed my optimum solution to 972. So whatever the arbitrary case may be, once I am getting 972 as the final answer, I have to instruct to the algorithm to stop. That is my focus. So every time I may not have all are different everywhere. So that might be some repetition. There will be 0 contribution to the function. That's why we are expecting everywhere a value which is less than this 972. So that will start increasing, say from 672 to 732, then gradually it will keep on improving its objective function value by using the genetic algorithm to get reached to the 972. Once 972 reached, it will stop, and that will be your final answer. So this Sudoku puzzle cannot have 2 different answers. It's a unique solution. That's why we can stop there 972 and we can declare the result. Okay. So the row fitness, column fitness, and subsquare fitness will be added together to give you the final fitness value, which is actually mathematically designed in this way. What I have shown here in the figure is written mathematically because it should be implemented into the computer to travel from one cell to another. So this is the column fitness, this is the subsquare fitness added together to give you the final fitness. That is row fitness, column fitness, and subsquare fitness added together to give you the final fitness, which is going to be 972. That is what I have kept fixed. Now we can think of how the genetic algorithm is coming to the picture. Now we can see that let us say these are 2 different arbitrary solutions, not the final solution, arbitrary solutions. So if it is an arbitrary solution, we can keep it in one string. So this is x1, this is x2. So there are 9 variables, say. Okay, 9 variables, and I'm going to create a population like this for the genetic algorithm. String 1. So string 1 says that you just cut this piece, this first row only, and put over here under the x1. There are 9 things. Okay, so this is gone there. Then you cut the second one and take it to the under x2, and so on. So all these parts has been gone there, and for the first string there will be how many cells? 9 into 9, 81 cells in the first row. So this will give you one function value, say 378 or something like that. Once I'm getting it 972, I will get, that is the use of the function value fijkl I have explained. So for every individual solution, it's not a solution of course, but we are trying for a solution, and individual entry we have done. So that individual entry will be treated as a string, and we can make a population. Okay, so the crossover is uniform crossover there, where each individual strings are going to be swapped. This part will be caught there, and it will be gone to the first. These are 2 strings actually, individual n and individual n plus 1. Individual means strings only. So n and n plus 1 individuals are there. So this row will be swapped, and this row will be unchanged. This row will be swapped, and so on. Alternatively, they will swap, because if everything will be swapped, then there will be no change in the individuals. That's why we are swapping alternative rows or alternative variables, you can say. So that is the main motto of the crossover, and where we have used the probability which is best suitable for this is 0.8 probability of crossover. Similarly, there is a mutation concept called bitwise mutation. If there is a 9, any arbitrary none given will be discarded and will be again inserted by 1 to 9, just to make a arbitrary swapping or arbitrary change in the arbitrary contribution, small contribution in the population. So the probability of mutation has been taken 0.2. There is another concept called alternate allelism, where all the before retrievable genetic algorithm and after the cycle, both the population have been merged together, and alternatively after sorting, alternatively the strings have been picked up. It's called alternative allelism, which works better there. And there is a important step called remove repetition. If there is a repetition in the given, then will be discarded and will be replaced by a number which is already not there. So that is the concept of remove repetition. Both in rows and columns, we have done the same exercise. So this is the whole idea of the algorithm, the flow chart of the algorithm. How we have moved everywhere. We have to check whether the solution found or not. The solution found means we have to check whether 972 achieved or not. Once it is achieved, it will direct it towards the stopping criteria to stop there. So it is called retrievable genetic algorithm based on this actually. These reset points actually. If the givens are very more, we are happy to fill only the few number of cells. It's called an easy level Sudoku puzzle. So if the number of givens are going to be very less, then the restart point is 2000. After 2000 iteration, we are going to restart the entire genetic algorithm. Because of this reset point, we are naming it as retrievable genetic algorithm. And what's better actually, and you can see the result there, where the success rate is going to be, this is the GM by Molter and Culgeron, with whom we are going to compare our rate GA. The percentage in success out of 100 different runs, the percentage of success is going to be increased everywhere. So there are 9 levels Sudoku puzzles actually: 1 star, 2 star, 3 star, 4 star, 5 star. Each is challenging, difficult, and super difficult level of Sudoku puzzle. So depending on the given, the reset point has been set, and we have seen that the success rate has been improved by rate GA as compared to GA in all of the cases. Similarly, the number of function calls, it is depending on the time actually. You can see that how small amount of function calls has been used for red GA over the GA. Of course, for super difficult and challenging problems, it takes almost or more number of function evaluations there. But in return, the success rate and function value are going to be better. You can see here the standard deviation also very good in retrievable GA, and that shows that it is stable, more stable than the previous one. Similarly, you can see the success rate by taking arbitrary Sudoku puzzles taken from the sudokupuzzle.com site. 2 types of easy number of Sudoku puzzles, 100 number of times. We have run that one. So success rate everywhere we have achieved the success rate, but for the medium level, the success rate is going to be gradually changed. If I'm moving towards easy to hard, the success rate is going to be reduced there. That's why harder for the human being is harder for the computer even to solve it, for retrieval genetic to solve it. But the other papers which are coming, upcoming papers, can compare these results afterwards. Anyway, we want to see how can you compare this, how can you solve this solution just by using my software. So this is an easy level Sudoku puzzle. Let us solve this by using the retrievable genetic algorithm. Just click on it, and it is asked you that you have to press 1 for easy level Sudoku puzzle. This Sudoku puzzle has been fed in text file inside this. So just to solve this puzzle, we have to press 1. This is easy level Sudoku puzzle. For medium, press 2. For hard, press 3. And if you are throwing some puzzles to me, that is an extra problem, I have to feed that in a text file to press 4 to run that one. So now it is 1 to solve it. You can see that only 10 number of iterations of the genetic algorithm needed by the retrievable genetic algorithm to solve it. But it is not unique, as you know that it is a random technique. If I am pressing 1 again, it will take 15 number of iterations, 5 more we got. Similarly, you can go back to the medium number of medium level Sudoku puzzle. Of course, it will take more time. I have to press 2 instead of 1 for this medium level. It will take more time. 441 number of iterations for GA, red GA to solve it. You can also cross check it. The givens are not changed here, and rest of the parts have been filled up, but it can also be changed again. If I will press once again, so only 241 number of iterations it took. Similarly, you can go for the hard level of Sudoku puzzle to solve it. So you have to press 3 to, it will take more time. It is 431 fortunately this time, but usually it takes more time. Now, yes, it is 417 for this hard level Sudoku puzzle. Okay, this is how we can design your own algorithm to solve your individual problems. For the time being, I'm happy actually, and I'm thankful to all the organizers to giving me a chance and opportunity to be a part of this workshop. And thank you.
Thank you, Dr. Kedar, for introducing such a vast from the beginning of optimization to the importance of the group activity in the population search, especially, and also introducing 2 new algorithms where all the participants may think about to develop a new algorithms if they wish, like DFO and TSO, which are the 2 new algorithms inspired from the nature philosophy. So if participants are willing to do and think about the natural phenomena, how the things are happening, they may think about to develop some new algorithms. With this one question we may take if the participants have. If anyone have one question, they may ask. Unmute and may ask if anybody have a question, please. If any participant have a question on this, then quickly 1 or 2 we may take. Okay. Okay. So with this again, we're not getting the question. So, okay. With this again, I would like to thank Dr. Kedar for giving valuable time and nice discussion in detail on this optimization and evolutionary optimization especially. All optimizations are very much needed in the machine learning and deep learning, and all the participants, those who are interested, may look up on these techniques and get the better how to use this. With this again, I would like to thank Dr. Kedar Nath for giving a nice talk during this workshop.
Yeah, thank you, sir. Thank you, Dr. Singh. Thank you, Dr. Singh, and thank you all the participants for present hearing. Thank you all. Thank you. Bye-bye.
Thank you, sir. Thank you giving the time. Thank you. Thank you. So all the participants, we have 10 minutes now. Okay, at 10:45, next session will be start, and it will be on Google Colab, how to use this machine learning regression and other techniques on Google Colab, how to do the coding and all. So it will be more our hands-on session. So you just take 10 minutes break, and again we will be assembled for the next talk at 11:45. Thank you.